Chips are getting faster every year, but AI systems are not improving at the same pace. The reason is not a lack of compute power. The real limitation is memory. This is often called the memory wall, and it is one of the most important constraints in modern computing. To understand this, start with how a typical AI system works. When a model runs, whether it is generating text, recognizing images, or making predictions, it performs a large number of mathematical operations. These operations happen inside processors like GPUs or specialized AI chips. On paper, these processors are extremely fast. They can perform trillions of operations per second. But those operations depend on data. The processor needs to constantly read model parameters, input data, and intermediate results from memory. This data is not stored inside the compute units themselves. It sits in different levels of memory, such as caches, high bandwidth memory, and system RAM. Every time the processor needs data, it has to fetch it. This movement of data takes time and energy, even though the processor is capable of running very fast. It often ends up waiting for data to arrive. This waiting time is where performance is lost. This gap between compute speed and memory speed is what creates the memory wall. Over the years, processors have become much faster, but memory speed has not kept up at the same rate. As a result, the imbalance has grown larger. In traditional computing tasks, this problem exists but is manageable. In AI workloads, it becomes much more severe. AI models, especially large ones, require moving massive amounts of data. A modern neural network can have billions or even trillions of parameters. Each parameter needs to be accessed multiple times during computation. Consider a simple example. If a processor can perform a calculation in a fraction of a nanosecond, but it takes several nanoseconds to fetch the required data from memory, then the processor is effectively idle most of the time. It is not limited by how fast it can compute, but by how fast it can receive data. This is why adding more compute power does not always lead to proportional improvements in performance. If the memory system cannot supply data quickly enough, the extra compute capacity goes unused. The memory wall is also closely tied to energy consumption. Moving data is often more expensive than computing on it. In many cases, the energy required to transfer data from memory to the processor is higher than the energy needed to perform the computation itself. This is one of the reasons why AI systems consume so much power. To address this, modern hardware designs include multiple layers of memory. The closest to the processor is cache, which is small but very fast. Then comes high bandwidth memory, which offers higher speed and capacity. Beyond that is system memory, which is larger but slower. Even with these layers, the problem remains. The total amount of data involved in AI workloads is so large that it can't all fit in the fastest memory. Data has to move back and forth between different layers, and each movement adds delay. High bandwidth memory, or HBM, is one of the key technologies developed to reduce this gap. It places memory closer to the processor and uses wider data pathways to increase throughput. This allows more data to be transferred at once. While this improves performance, it does not eliminate the problem. It also increases cost and complexity. Another approach is to redesign how computation and memory interact. Instead of moving data to the processor, some systems try to move computation closer to where the data is stored. This concept is often referred to as near-memory or in-memory computing. The idea is to reduce the distance data needs to travel. There are also software-level solutions. Techniques like quantization reduce the size of the data being processed. Smaller data means less movement and faster transfers. Other methods, such as model pruning and compression, aim to reduce the total amount of data required for computation. Despite these improvements, the memory wall continues to be a major challenge. As AI models grow larger, the demand for data movement increases. This creates a situation where improvements in compute hardware are not fully realized in real-world performance. The impact of the memory wall can be seen in both training and inference. During training, models process large datasets repeatedly, which requires constant data movement. During inference, especially at scale, the system must serve many users simultaneously, each requiring access to model data. In large data centers, this leads to a significant increase in infrastructure requirements. More memory, faster interconnects, and advanced cooling systems are needed to handle the load. These factors contribute to the rising cost of running AI systems. The memory wall also influences how future hardware is designed. Companies are no longer focusing only on increasing compute power. They are investing heavily in improving memory bandwidth, reducing latency, and optimizing data movement. This shift can be seen in the design of modern GPUs and AI accelerators. Features like larger caches, faster memory interfaces, and specialized interconnects are becoming more important. The goal is to keep the processor fed with data at all times. In simple terms, the memory wall means that performance is no longer limited by how fast a processor can compute, but by how fast it can access data. This changes the way systems are built and optimized. Looking ahead, solving the memory wall will require a combination of hardware and software innovations. New memory technologies, better system architectures, and more efficient algorithms will all play a role. The key point is that the future of AI performance will not depend only on faster chips. It will depend on how efficiently data can be stored, moved, and accessed. Until that improves significantly, the gap between theoretical performance and real-world performance will remain. This is why, even as chips become more powerful, AI systems do not scale at the same rate. The limitation is not in the ability to compute, but in the ability to deliver data to that computation fast enough.